Hey hey guys, this is our MPC project on the applications of MPC for automated speed control of a treadmill. Traditionally, treadmills require you to press a button to change speed, but automated treadmills will automatically adapt to match the speed of the user. However, the treadmills currently are very jerky and not very great for user experience, so the goal is to make the speed change as smooth as possible with two methods. One is tracking the user's desired speed and minimizing the jerky acceleration. We're doing this using two methods. One is using the acceleration as the input, and second is the change in acceleration as the input. And we'll be evaluating the two and seeing which one is better. Approach A models the treadmill as a single integrator. It only takes the velocity error as the state variable and takes the acceleration from the motor of the treadmill as the control input. We have state and input constraints just to maximize the safety of the user and their experience. Approach B is two-dimensional. It takes the velocity error as one of the states, but also the acceleration of the treadmill. The change here is that the control input is the acceleration change that is commanded, not the actual acceleration. We still have similar velocity and acceleration constraints, but we also have a new input constraint on the change in acceleration. This is again to maximize the safety and of the user and their experience.
We designed an MPC controller for each approach, and for both cases, we have quadratic cost and linear constraints. The goal with the MPC design is to minimize deviations from the user's desired speed through the state weight Q, and then for the MPC controller for approach A, the input weight R assigns a cost to the excessive acceleration inputs, and the MPC controller for approach B, the input weight R assigns a cost to excessive changes in acceleration or jerk. In both cases, recursive feasibility is achieved by assigning the terminal set to the maximal positive invariant set computed under a discrete time linear quadratic regulator. And then stability is achieved through the terminal cost by designing it as the solution from the discrete time algebraic Riccati equation. We performed a first simulation where the time step is 3.5 seconds and the MPC prediction horizon is n equal to 3. And this simulation runs the MPC controller for a total of 25 time steps. And the initial velocity error is set to 0.5 meters per second, which means that the velocity of the treadmill is 0.5 meters per second faster than the desired velocity by the user. For the MPC controller for approach A, the result is a plot that shows the evolution of the velocity error over time. And we see that the controller effectively brings the error to zero. And for approach B, the result is a plot that shows the evolution of the velocity error and the treadmill's acceleration jointly. And we see that both states converge effectively to zero too. And then we performed a different type of simulation where this time the user's desired velocity varies over time according to the profile that we show on the slide. In these cases, the MPC controller ran again with a prediction horizon of n equal to 3 and tried to adjust the treadmill's velocity to track the desired value. And we tested different scenarios, varying the tuning weights for the state weight Q and the input weight R. And on the next slides, we'll show the results.
Okay, now let's discuss the results of simulation 2, where we tested the performance of MPC-A and MPC-B under three different cases as explained by Alex by tuning different weights of state penalty Q and input penalty R. So let's start with the first case A, where Q equals to 1 and R equals to 1, representing a balance scenario. In this case, the velocity error reduced smoothly over time and the treadmill tracks the user's desired velocity with minimal lag. You can see in the graph, the maximum velocity error observed is 0.62 meter per second and the maximum jerk is 0.39 meter per second cube. This case demonstrated a good trade-off between tracking accuracy and the smooth control inputs. Now case 2A. We increase the Q to 5, prioritizing the tracking accuracy while keeping the R equals to 1. The velocity error reduced more aggressively, resulting in a lower velocity error of 0.38 meter per second. However, this comes at the cost of increased jerk, which rises to 0.66 meter per second cube. It is ideal for the application where the quick adjustment are critical, even if it compromises the smoothness. Now we'll discuss the case 3A. For case 3A, we keep Q equals to 1 and R equals to 2, emphasizing smoother control over tracking performance. Here the jerk reduces to 0.3 meter per second cube, but the maximum velocity error increased to 0.882 meter per second. So this case achieves the smoothest control for MPCA, but it sacrifices tracking accuracy significantly. Now we'll move to MPC B, starting with case 1B, where Q equals to 1 and R equals to 1. In this balance scenario, the maximum velocity error is 0.52 meter per second, slightly better than MPC A's performance. The maximum jerk is significantly lower at 0.11 meter per second cube, providing the smoother control. This case offers a better trade-off between tracking accuracy and the smoothness compared to MPC approach A. Now for case 2B, Q is increased to 5 with R remaining at 1, prioritizing the tracking accuracy. The maximum velocity error reduced to further 0.4 meter per second, while the maximum jerk remains relatively lower at 0.17 meter per second cube. MPC B in this case outperforms MPC A in both tracking accuracy and the smoothness, making it excellent choice for responsive control. Now, finally for case 3B, where Q equals to 1, R equals to 2, focusing on smoother control inputs. Here, the maximum jerk is the lowest at 0.09 meter per second cube, but the maximum velocity error increased to 0.60 meter per second, reflecting the reduced tracking performance. This case achieves the smoothest control for MPC B, and it also performs a better MPC A, but it has higher maximum velocity errors.
So in conclusion, we found that increasing the state weight in the cost function improves tracking accuracy, but leads to higher levels of jerkiness. On the other hand, raising the input penalty smooths out changes in control input, yet allows more deviation in velocity. Balancing these weights results in a solid compromise, leading to accurate tracking without excessive roughness. Moreover, the improved MPC-B approach clearly outperforms MPC-A, delivering significantly lower jerk and reduced velocity errors. Furthermore, the additional complexity and storage required for MPC-B are minimal, making it a very practical choice overall. Thank you so much.